So, hi everyone. I will be presenting on a topic called Generalized Bures Wasserstein geometry for symmetric positive definite matrices and remaining optimization. So, my name is Andy Han, and I'm from University of Sydney. And this talk mainly concerns two of our works in collaboration with Banda Pratik from Microsoft India, and also Jim Beam, which is my supervisor. So these are the two of my our works that I'm going to cover in this talk. So one is in the NeurIPS 2021, and another one is this a GSI paper. Okay. So learning over SPD matrices has many applications in a variety of fields, including the metric and kernel learning, medical imaging, in particular the diffusion tensor imaging, and natural language processing, computer vision, and also domain adaptation, and so on and so forth. So the SPD matrices with the Euclidean inner product can be turned into a Riemannian manifold, but the naive choice of the Riemannian the Euclidean metric can be problematic. So, for example, it may incur the negative swelling effects when you want to interpolate between several SPD matrices. So this has many has led many works to actually develop various metrics on SPD matrices. But firstly, why do we need so many metrics? So the first is to choosing different metrics may bring distinct features that may benefit or harm the interpolation, averaging, and doing statistics estimates for SPD matrices. And also, it in fact will impact the design of learning problems, for example, using some notion of distances, which comes naturally from the choice of suitable Riemannian metric. And choosing different Riemannian metrics may fundamentally change the search space geometry for Riemannian optimization as well. So that is what we wish to solve, an optimization problem with the variable constraint to be positive definite. And so different metrics can affect how we define the notion of gradient, how we update variables, etc., which largely affect the convergence speed of numerical algorithms. And this is what we're going to focus on today, so which is on the Riemannian optimization aspect of choosing Riemannian metrics. So since we focus on the aspect of geometry for Riemannian optimization, so here I'm going to summarize some of the basic preliminaries on Riemannian optimization for those who are not familiar with this topic. So a Riemannian manifold is a smooth manifold with a smooth inner product structure, which is known as the Riemannian metric. And this metric induces a norm on the tangent space, which can also define geodesic. We can also define geodesic, which represents the generalized straight line segment. And this also leads to the notion of exponential map, which is defined as the endpoint of a geodesic. So optimization over a smooth manifold constraint can be achieved with techniques from Riemannian optimization. So for this purpose, we require the notion for Riemannian gradient, which is defined with respect to the Riemannian metric. So with the gradient information, Riemannian steepest descent is an iterative algorithm that updates the variable x in the direction of the negative Riemannian gradient using the exponential map. And we can also design the second order methods as long as the Riemannian Hessian is well defined. And then we can adapt techniques from transposition methods to design Newton types of updates on manifolds. Okay. So as we can see, the proper choice of Riemannian metrics is very important as it will affect how we update variables. So there exists many Riemannian metrics, including the FI invariant, log Euclidean, log det, log Cholesky metrics, etc. So out of all the developed Riemannian metric, it seems that the FI invariant metric has been the most popular one, especially for Riemannian optimization. So this is primarily because on the AI metric and the FI invariant metric, the Riemannian optimization ingredients like the Riemannian gradient, the Hessian, and exponential map can be computed very efficiently. And many problems that are geodesic convex under this metric, which allows faster convergence to global optimality. So which is a very good thing under this metric. Also, this metric, it seems to be the only available geometries in many toolboxes that are specifically designed for optimization of manifolds. Okay. And there's a more recently proposed but less explored remaining metrics called the Bures Wasserstein geometries, which actually originates from the Wasserstein distance between Gaussian densities. So in the first work, we actually show this BW geometry provides a viable and often better alternative to the default affine invariant geometry when optimizing over the positive definite matrices. So here we compare the ingredients of the remaining optimization under the two metrics. So we see that all the ingredients can be computed in relatively the same cost. So for the affine invariant metric, the most computable the most computational the bottleneck is the matrix exponential, while for the Bures Wasserstein, the bottleneck is the solution to the matrix linear system, which is known as the Lyapunov operator. So one key motivation of the first work is by dissecting the metric dependence on the base point x. So for the affine invariant metric, we can rewrite the metric in a vectorized form such that the metric tensor is the inverse of x O times x. So where this O times symbol represents the canonical product. So on the other hand, the Bures Wasserstein metric has a metric tensor which is inverse of O of x O plus x. So this O plus here represents the canonical sum. So it is clear that the BW metric only has a linear dependence on the base point, while the AI metric has a quadratic dependence. So this quadratic versus linear dependence on x should affect especially the conditioning of the algorithms around the optimal solution, and especially when x is an ill-conditioned matrix. So this observation can be formalized in this lemma here, where we analyze the condition number of the remaining Hessian at optimality. So the condition number of remaining Hessian corresponds to the ratio of largest to smallest eigenvalue. So here we denote kappa star to represent the condition number of the remaining Hessian under both affine invariant and BW geometries. So here we see that the condition number of AI is bounded according to the quadratic of condition number of x star, which is actually the optimum point. But under the BW geometry, we see the condition number is bounded in terms of just the first order of the condition number of x star. So this formalizes our observation in the previous slide. Also, we can see here that the condition number bound also depends on the condition number of the Euclidean Hessian, this hx star. So the consequences of these bounds are that for the linear function, quadratic function, the higher order polynomial functions, we can actually show the condition number on the affine invariant geometry is larger than BW, especially for ill-conditioned x star. But also we find an example of the log det function, which means the log of determinant of the matrix. So this function has a condition number. So the condition number on the affine invariant geometry is actually smaller than BW. So this is particularly due to the special structure of the Hessian of this function. But this will be addressing. So we'll be addressing this issue of BW in particular this second work that we're going to see later. So apart from the condition number of BW versus AI geometries, we can also show that for BW, because it is a non-negatively curved space, it comes with a smaller curvature constant zeta in the following trigonometry distant bound. So this bound has appeared commonly for analyzing first-order algorithms on manifolds, as we can see later. So a smaller bound usually results in a faster convergence rates that can be obtained. And also, the BW preserves the geodesic complexity for many interesting functions, which suggest if we want to switch from affine invariant geometry to BW for these functions, then we're not losing anything, right, in terms of the convergence guarantees. So we here formalized the impact on the conditioning on the curvature in terms of the convergence of Riemannian descent and also the remaining trust region, so which are the two representative numerical solvers for Riemannian optimization. So we see for both the first and second order methods, smaller condition number at optimality is better, as we can improve the convergence rate. And additionally, for the first order algorithms, so we can see the impact of the curvature here, where the smaller curvature constant ensures a faster convergence rate. Okay, so this is also we do a bunch of experiments, and in order to verify our claims, so we compare the convergence of algorithms under different geometries. So here we also include the log Euclidean, this LE geometry, as a baseline, although it's less computationally efficient. So we see here that the BW outperforms affine invariant and the log Euclidean on a variety of problems, such as the weighted least square problem, the problem of solving the Laplace equation, and trace regression and metric learning, etc. But for the example of log determinant maximization and also the Gaussian mixture model, we see the affine invariant has a better performance compared to BW. Okay, so now that we have seen the comparisons between affine invariant and BW metrics for Riemannian optimization, we observe that for some functions, BW has better conditioning, right? While for other functions, like particularly for the log det function, affine invariant has a better conditioning. So a natural thought would be, can we find something in between where we can actually change some parameterization of the metric and recover both the metrics so we can get the benefit of both worlds? So this, however, is inherently difficult particularly because the two metrics are different in terms of the curvature. So the BW is actually non-negatively curved, while the affine invariant is non-positively curved. So it seems to be difficult to merge these two in one parameterized form. But here we still want to solve this issue, so we can write out the metric first. So here we record the expression of the two metrics, where AI metric involves x O times x, while BW involves O x O times I identity. So this I means identity matrix. And therefore, a natural generalization is to replace this identity matrix in BW with an arbitrary SPD matrix M. So this is exactly what we are doing here, which is to introduce the generalized BW matrix, which is parameterized by this matrix M. Okay, so here we can see that BW can be computed by solving a generalized matrix inequality, and also we can generalize matrix equality, and we can also show that the remaining distance under the GBW matrix arises naturally from solving the generalized orthogonal Proclus problem and from the generalized Wasserstein distance, where the distance is replaced by this Monobius null parameterized by this matrix M. Right, so and in this work, in the second work, we actually derived all the expressions for the remaining geometric ingredients, including the distance, remaining distance, the geodesic expressions, an exponential map, inverse exponential map, also known as the logarithm map, and also the remaining connection, and also the minimum and maximum curvature, which basically completes the geometric aspects of this geometry, of this new proposed metric. And right, so in this paper, we also connect the formulation of GBW to various problems of interest, including the robust BW distance, the BW behavior center, and the interpolation and geometry over PCA. But here we only focus on, for this talk, we only focus on the application to Riemannian optimization. So for this purpose, we also derive the remaining gradient and the Hessian of the real value function under this proposed geometry, and show that actually the many functions we have considered earlier are still geodesic convex under the new GW matrix, actually for any choice of m. Okay. And in particular, the GBW geometry is flexible in terms of the choice of m that parameterize the metric. So in the special case, when m is equal to x, so we can see the expressions of the remaining gradient and the Hessian coincides with the two metrics, especially coincides with the Fi invariant metric up to some constants. So, and also we see the expression of the exponential map of GWW is that in fact the second order is in fact a second order approximation to the exponential map of the Fi invariant metric. So this suggests that GBW locally coincides with AI geometry for the purpose of Riemannian optimization, and this can be corroborated in experiments. So for the experiments, we have done this log-dat maximization problem and also the GMM variety of data sets. So we can see that by simply choosing this m to be x, GBW leads to a significant improvement over the vanilla BW metric, and while performing similarly and sometimes better than the Fi invariant for the log-dat and GBW problem. Okay. All right, so that's all for my talk, and thank you very much. So, so if you have any questions, so please feel free to ask. So, hi everyone. I will be presenting on a topic called generalized Bures.
So Bamdev, can you hear me? Okay. So this is the room. So Bamdev, I should say, had a great role in my trajectory because I picked my PhD supervisor because I went to a talk he gave as a postdoc in Cambridge, and his supervisor was Rudolf Teppelker, and I liked to talk so much that I thought it's a good idea to do a PhD with Rudolf. And that's how I got into the GSI orbit as well, through Rudolf. So if there are any questions, I can just sort of pass it on, and then hopefully you can hear his response. Thanks for your time, by the way, Robin. Any questions? Come on, I hope. Yes.
Hi, thanks for the video. Is it a coincidence that using matrix X in the GBW looks like the affine invariant metric?
Did you follow that? Found it?
Yes, I followed it. I heard the question, and thank you very much for this question and for this opportunity, Cyrus, and the organizers. I'm so sorry I'm not able to be there in person. Now, coming back to the question, right? So this is not at all a surprise that for m equal to x, we actually locally behave like so the GBW actually locally behaves like the AI metric. So that is not completely unexpected. What is unexpected is the performance of BW improves. So from a numerical optimization point of view, what we really do is that, instead of selecting one m throughout the iteration, so think of an algorithm where m is being changed dynamically. So even though we do not select the m at the current iterate, we can still manage to select, let's say, the m of the x that was like 10 iterations ago, and yet GBW gives a much better convergence performance. So that was something surprising for us, that so these geometries, which are fundamentally different, right, in terms of the curvature, this somehow, with parameterization, with numerical techniques, they can still made to be, made to work similarly. So that was the surprising aspect. Not really that, plugging the expression will recover the AI expression. Yeah.
Right, thanks. Could people hear that response, more or less? Okay, great. Any other questions? I kind of have one, actually. The curvature is kind of surprising, that there was a statement that a lot of functions remain geodesically convex when you go from AI to BW, given that they have different curvatures. That's quite surprising. Do you have intuition for somehow how that works?
Not really, Cyrus. So I don't have much more intuition. It's just that we were playing with the expressions and we found them. And many of the functions actually turn out to be Euclidean convex also. So maybe they are convex in a big regime.
Mm-hmm.
Yeah.